Inside a laboratory at Oxford, something impossible has taken place. Information has leapt across distance without moving at all. A gate has opened, not of steel, but of thought itself. For most of history, teleportation lived only in stories and dreams, where matter dissolved and reappeared somewhere else. But reality is quieter, more unsettling. This is not the movement of objects. It is the transfer of what makes them real, their hidden state, their logic. In this still moment of discovery, the boundaries of distance tremble, and the very meaning of connection begins to change forever. The idea of teleportation. Teleportation has always lived in our imagination. We think of characters vanishing in a flash of light and reappearing somewhere else. That picture belongs to fantasy. What Oxford has demonstrated belongs to physics, and it is far stranger. Here, nothing material is transported. No object crosses the space between. Instead, what moves is information, the hidden code that defines how something exists in the quantum world. The key is entanglement. When two particles become entangled, they are no longer separate. They share one existence, no matter how far apart they are pulled. Change one, and the other reflects it instantly, as if the distance between them did not exist. There is no signal traveling in between, no hidden thread. It is a connection without movement, a presence without contact. Einstein once admitted discomfort with this idea, famously calling it spooky action at a distance. To him, it seemed almost impossible that reality could behave this way. Yet over time, experiments confirmed it again and again. Entanglement is real, measurable, and repeatable. This strange bond makes teleportation possible. By using entanglement, scientists can transfer the quantum state of a particle from one place to another without the particle itself ever moving. It is not science fiction, but something quieter, a leap of information that defies distance, a whisper carried by the very laws of nature. Oxford's breakthrough. For years, scientists had used teleportation to transfer single quantum states from one place to another. That was already remarkable. It proved that information could slip across space without wires, signals, or motion. But what happened at Oxford pushed this idea into an entirely new world. Instead of teleporting a single state, the researchers managed to teleport logical quantum gates, the actual tools that perform operations inside a quantum computer. Think of it as the difference between sending a single word across a line and sending the rules of language itself. With this step, the two processors involved were not just sharing data, they were sharing the very instructions that allow them to think. This had never been done before. It meant two separate quantum processors could act together as if they were one machine, even without a direct connection. In that quiet Oxford lab, computers learned how to reach across space, not with wires, but with the language of the universe itself. Why logic gates matter. Every computer we use today, no matter how advanced, is built on tiny switches called logic gates. These gates decide what happens to streams of ones and zeros. They form the heart of every phone, every server, every machine that calculates or stores information. Without them, nothing works. In the quantum world, these gates become something far stranger. Instead of handling simple ones and zeros, they work with qubits, particles that can be many things at once because of superposition. A single quantum gate can explore possibilities far beyond the reach of classical logic. They do not just decide yes or no, they hold the space between and all the hidden patterns it contains. That is why Oxford's achievement matters. To teleport logical gates is to allow two quantum machines to share their power directly. It is as though two minds learn to think together without speaking. No wires, no signals, only an invisible bridge made from the laws of physics themselves. The scalability problem. Quantum computers today are fragile creations. They sit inside chambers colder than outer space.
However, quantum computers is bigger than that. Quantum computers is a hardware question.
Shielded from noise and light, each qubit must be held in balance, like a candle flame that flickers at the slightest breath. The more qubits we try to place on a single chip, the harder it becomes to keep them stable. Errors grow, signals blur. What begins as precision turns quickly into chaos. This is the central barrier of the field: scale. A handful of qubits can demonstrate the strange power of quantum mechanics, but true breakthroughs demand thousands, even millions. Building one massive chip to hold them all has proven close to impossible. The systems become noisy and collapse under their own weight. Oxford's discovery points to a different path. Instead of forcing everything into one fragile device, we may link many smaller processors together. Each one is stable on its own, yet connected through teleportation. Like separate instruments joining in harmony, they could form an orchestra of quantum power far greater than any single piece alone. The modular quantum future. The promise of Oxford's work is not just in the experiment itself, but in the vision it opens. If processors can be joined without wires, then we no longer need to force all power into one fragile core. We can build smaller, steadier units and let them speak through teleportation. Imagine clusters of these processors scattered like stars, yet bound by invisible threads. Each one is limited on its own, but together they act as a single system. Problems that overwhelm classical supercomputers could be divided across this network and solved as one. What once looked impossible suddenly feels within reach. This idea is more than technical progress. It is a change in how we think about computing, not a monolith, but a constellation. Not a single tower of complexity, but a field of simple parts woven into unity. With such modular designs, the dream of a quantum superbrain no longer belongs to distant speculation. The pieces can be built today, then linked tomorrow, until the whole is greater than anything we have ever known. Quantum Internet. There is another layer to this breakthrough, one that reaches beyond computing power. It is the possibility of a new kind of internet. Today, our networks rely on classical signals and mathematical codes to keep information safe. Encryption works because certain problems take too long for normal computers to solve. But once large quantum machines arrive, those codes will not hold.
And here at Google's Quantum Computer Lab in Santa Barbara, California, that future is right around the corner.
Secrets that seem unbreakable today could be exposed in seconds. A quantum internet would change this. Instead of relying on hard problems, it would rely on the laws of physics. Messages would be carried by entangled particles, where any attempt to intercept them would leave a trace. The act of eavesdropping itself would disturb the system, making spying impossible without being caught. This means communication that is not just private, but fundamentally protected. Banks, governments, and hospitals could all send information with a certainty no wiretap could pierce. It is a world where security does not depend on trust, but on the unshakable rules of nature, and Oxford's teleportation experiment is one of the first steps toward building it. The challenges ahead. As promising as this work is, the path forward remains steep. Qubits are delicate beyond imagination. Heat, sound, stray fields of energy, almost anything can collapse their fragile state. Keeping them coherent long enough to process information is like trying to hold mist in your hands. Then comes the problem of mistakes. In classical systems, errors can be corrected by copying and checking data. But in quantum mechanics, copying is forbidden. The very act of observing changes the state itself. New methods of error correction must be designed, ways of protecting information without destroying it. There is also the question of distance. The Oxford team showed teleportation between nearby processors, but building a global network will demand far greater stability. Entanglement must survive across cities, even continents. That has never been done at scale. So the dream is not yet realized, but the first door has opened. Each challenge ahead is vast, yet no longer impossible. What was once a theory is now a map waiting to be followed. The bigger picture. This experiment is more than a clever trick inside a physics lab. It marks a turning point in how we see quantum mechanics itself. For decades, the subject lived mostly in theory, strange equations written on blackboards, experiments that confirmed ideas but offered little to everyday life. Oxford's teleportation of logical gates shows something different. It shows that these abstract rules can be shaped into real tools. We are watching physics turn into engineering. The same laws that once puzzled Einstein are now being used to build machines that think in new ways. It is not only about faster answers, it is about creating a form of computation that does not resemble the computers we know at all. In this light, the work at Oxford feels less like an isolated achievement and more like the first chapter of a longer story. A story where technology begins to merge with the hidden order of reality itself, and where the boundaries of what we call possible continue to shift. Inside Oxford's lab, a small experiment has hinted at a larger future, not of machines made heavier and stronger, but of connections woven from silence and distance itself. Teleportation is no longer just an idea on paper. It is something we can now build upon. The road ahead is uncertain, filled with challenges that demand patience and imagination. Yet the direction is clear. Computing will not simply grow faster, it will grow stranger, deeper, and closer to the fabric of reality. This is only the beginning. The rest of the story is waiting to be written.